So in this lecture, we're going to see about relativistic superstrings. So far we've seen about quantum open strings, quantum closed strings, and as I said, we saw these strings only can describe a bosonic state. Okay, a bosonic state where an exchange of a state will, the property of a boson is that you exchange two states. The wave functions are symmetric, right? In quantum mechanics, you studied that you exchange two states, there is a symmetry, right? But in a fermionic states, they are the two states by exchange, they will gain a negative sign, right? So they are anti-symmetric. Two states are anti-symmetric with respect to each other. So this cannot be described by whatever that we have studied so far. So far, what we've studied can only describe bosonic uh, particles or bosonic states. So real world string theory must also describe fermionic particles, right? So fermionic states. So that is what we will set out to do. So a candidate that does that is something called supersymmetric superstrings, and the superstrings need to have this property called supersymmetry. That means at each mass level, right? So we've studied about the mass square operator. So the mass square operator produces a spectrum of mass levels. Okay, so in the different so it produces a spectrum of mass levels. But at each mass level, what it says is the super according to supersymmetry. If you're using superstrings, then the bosonic and fermionic states must be equal to each other. They must have the equal number of fermionic and bosonic mass states at every mass level. Okay, so this is not found in nature. So what people think is we've studied about the spontaneous symmetry breaking, right? So when we studied about quantum field theory in our lectures, we had studied about spontaneous symmetry breaking. So they think this symmetry is also spontaneously broken. So it's still at a research level area, all these things. So there are people divided on both sides. So some people believe that this supersymmetry theories are attractive candidates for physics that lie beyond the standard model of particle physics. Okay, so let's go into seeing what this is about. So remember, this is the action that we wrote out, and we add another term to this action that denotes our action for the fermion. So this is the Dirac action for the fermion. So just like how we proceed to obtain our equations of motion from any action, we minimize the action, and at the endpoints they must. So these are the endpoints, and at the endpoints the variation should vanish, and and to arrive. So the condition that we get out of when we impose that condition, what equations satisfy that condition will give you our equations of motion. So when we impose that condition that the action, we minimize the action, and we say that the variation vanishes at the endpoints, we obtain our equations of motion. So here you can directly read off this from these equations are equations of motion. So here we can see this is, let's consider these two equations first. So these two equations give us our psi1 and psi2 are, they give us our left moving and right moving wave. So here you can see this is a right moving wave and this is a left moving wave. And then we also have another condition that because these must vanish at the bound at the endpoints, right? The variation should vanish at the endpoints. That means this equation also must go to 0. Therefore, such that the variation del of s goes to 0, then this equation also must go to 0. Then we arrive at this condition. Now the boundary points, we said, you remember that we said that the left moving and right moving waves are related to each other by we relate the two solutions by the boundary conditions. So this is what we arrive at. So the boundary conditions relate the left moving and the right moving wave. So psi1 and psi2 are related by the boundary condition. So what we find is there are two sets of equations that we can actually obtain from this, or the solution breaks down into two subspaces or two sectors. One equation where you can, so these are actually two equations where it combined and written into one equation. One reads off with the sign on the top, one reads off the sign in the bottom. You might have seen equations like this. So one equation is symmetric with respect to the boundary condition, right? So the next equation, what happens is, for the next equation, you can see at the boundary, it changes sign, right? So at the boundary, you can see that the second equation will change sign. So this is the second equation and this is the first equation. So both are combined and written into one. So this, here you can see that at the boundary condition, here the equation, they change sign, right? The two solutions. So it breaks into two sectors. So the first equation is called the Raman sector, and it arises from the top choice of the sign. And the second equation, or second subspace, it breaks into, or the solution breaks into two subspaces or two sectors. The second sector is called the Nevu-Schwarz sector. Okay, so these are the two sectors. So Raman and the Nevu-Schwarz sector. So R, and they denoted by R and NS. So we'll have to discuss the solutions in these two sectors, right? So just like what we said for our closed strings, these are going to obey the periodic conditions, right? The Nevu-Schwarz sector is going to obey the periodic condition, because at the boundary you can see that, oh no, sorry, so the Nevu-Schwarz sector changes sign at the boundary. So here you can see the Nevu-Schwarz sector is the one that the state that uses the lower choice of sign. So this is this equation. So at the boundary you have the these equations are changing sign. So it changes sign at the boundary. So that means you can expand it again in a form of a exponential, complex exponentials, and you have these uh, coefficients. These coefficients are what we will convert to operators. So when you convert them to operators, you quantize the theory, and then you have the mass square operator. So here this alpha refers to our bosonic states, right? We wrote out the action here, right? So this was the action we wrote earlier on, and these alpha were, so we were so long working on working with those quantum closed and open strings, where we were talking about states that can only describe bosons, right? So but this is going to describe bosons and fermions, right? So each mass level, we said there are equal number of bosonic and fermionic states. So this is our this corresponds to the Nevu-Schwarz sector, uh, the coefficients, and these are all operators, right? So these are all operators, and a state, a state can be, a Nevu-Schwarz sector state can be described this way. Okay, so here we have the P plus, we remember the light cone coordinates, and the PT refers to the transverse coordinates, right? So, and this is called a tensor product or a direct sum, okay, of states, a tensor product or direct sum of states. And here the summation is over. Here you can see this is actually a product, right? So a product that has a summation. So so here we are only talking about a 10-dimensional space time, and therefore here you can see the transverse coordinates are going from 2 to 9. Okay, so transverse coordinates go generally if you have 10-dimensional space time, you go from x0 to x9, right? So x1 and x1, x0 and x1 are written in terms of your light cone are used to write your light cone coordinates, and x2 to x9 is your transverse coordinate. So that here we have the product that is summed over from 2 to 9, that corresponds to the transverse coordinates, and then we have the sum over the states or the modes, okay, or the modes of the we are talking about the moded expansion, right? The moded expansion of your solution to your strings, which we quantize by converting these exponentials to operators. So it refers to the mode of the oscillator. Okay, it refers to the mode of the oscillator, right? So here you have sum going from 1 to infinity, and here we have fractionals. Okay, so it goes from z plus half. So z is any integer, and then we have we sum. So this goes as a half plus 3.5 plus, again you have, so z, you can see that z refers to, so z is your integer and you just plus half, and the sum is the summation here is over uh, z, right? So you go from 1 2 3 like that, and with that you just add half, so this becomes fractions. So the summation here is over a fraction. The summation of this product is over fractions. And similarly for the Riemann sector. Okay, so similarly for the Riemann sector, you write it in, this is the mode expansion, and then we convert them into, to quantize it, you convert the coefficients to operators, and then we have our mass square operator, the bosonic, this is corresponding to the bosonic state, and this is the fermionic state, and then we have our how we represent a state. So this is how you represent a state space in the R sector. Okay, so that is what we have. So an open string has two sectors, right? So we said the solution breaks into two subspaces, NS and R. Now closed strings are going to be formed by, just like how we did in the earlier case, we can form closed strings by combining left moving and right moving sectors of NS or R. Okay, so you just combine left moving and right moving sector, you will get a closed string. Okay, so so we have so we can combine the NS or R of two left moving and right moving sectors in four ways, right? So you can see that you can combine them in four ways. So a space-time boson in for an open string arises actually from an NS sector, and space-time fermions arise from a R sector in the case of open strings. But in the case of closed strings, space-time bosons actually arise from NS sector and also from RR sector, and space-time fermions arise from NS R sectors and R comma NS sector. So here you can see that a type 2A supersymmetric theory is formed by combining these sectors in these four different ways. So you just take left moving and right moving sectors and of NS or R, and there are four ways to combine them. So that is what you have. And here you can see that we have the equal number of bosonic and fermionic states. So remember I said a supersymmetric theory must have, so this is very important for a supersymmetric theory, right? So supersymmetric theory must have equal number of bosonic and fermionic states, right? Equal number of bosonic and fermionic states. So here you can see, as we said, the NS comma NS and R comma R sectors give rise to space-time bosons, right? So here you can see, and NS comma R and R comma NS sectors give rise to fermionic space-time fermion. So here you can see that they give rise to equal number of space-time on equal number of bosonic and fermionic space-time states. Okay, so equal number of bosonic and fermionic states, space-time bosonic and fermionic states are, you can see that this way of combining the sectors give rise to this type 2A supersymmetric theory. So there are different ways to combine these sectors, just like how we did here. There are different ways to combine these sectors, and all these different ways correspond to different types of supersymmetric theories. Okay, so there is type 2b, there is E2, there is our heterotic supersymmetric theories, and there is still more. There is type 1, and this is a area where current research is happening, right? So the literature will expand, and you will actually see a lot more than what is being taught here, actually. So this concludes the series of lectures where we've seen about uh, quantum. We've seen about an introductory level material on string theory, right? And as I said, this is a current area where a lot of research is happening, and so this is just an introductory series of lectures, and which, if you were to supplement with some of the textbooks, it will fill in with the theoretical gaps, which I haven't gone in very detail, because I just wanted to string out a grand narrative for string theory and leave a little bit of the, so that you don't get lost in the theoretical detail, but understand what is the grand narrative that's coming out of it. And then if you're able to now, if you're able to understand with so this much that we've explained so far, uh, with along with if you supplement it along with the study of your textbook, then you will be able to go into the current areas of research, and you'll be able to understand what's happening, and eventually, if you make progress even, right? So eventually you have to add to the knowledge that is already existing. So so thank you for watching this series of lectures. So if you do like our channel, do subscribe. That is what supports us. And please let your friends also know that there is something like this around. Thank you for watching. Bye bye.